Hello again. Welcome back to more lectures about physics. Today we're going to talk more about light, as I mentioned before. This is kind of the final topic. We're mostly just talking about light, and as I mentioned earlier in one of the past lectures, it's the study of light that really sort of transitions us into talking about modern physics, so things like quantum mechanics and nuclear physics and relativity, things like that. So we had two lectures just about light. Light is very interesting in itself, and we did also about different wavelengths of light and the whole electromagnetic spectrum, reflection of light, refraction of light. So, all kinds of stuff about light. We got one more lecture here, but this is largely going to be about the properties of light that didn't sort of fit into, or nicely into categories before, say, the early to mid 1900s. Yeah. So I called this lecture Light Quanta, and hopefully start to make sense why. Quanta is like a word that basically means like an amount, a specific amount, size of something, a piece of something. And yeah, so let's just keep going. Okay. So in the end of the last lecture, we were talking about reflection and refraction of light. So reflection being basically when light encounters a surface and it bounces off, like mirrors. Refraction was when light was encountering a surface, but it moves through that surface, so say from one material to another, like air to water, and it tends to turn a bit as it goes from one material to another. So as it crosses that sort of boundary, from the surface boundary here, it makes a bit of a turn, either down or inward or outward, depending on the change, or which material it goes from where to where. Right. So there's another thing that light does, and actually, just as reflection and refraction are not confined to just light waves, there are all kinds of waves do this, or do those things. Diffraction is something else that light will do, and also all other kind of waves will do. But it's not the same as reflection or refraction. So diffraction is a particular thing that happens when a wave basically encounters an obstacle of some kind. And it's not bouncing off of it, and it's not going into it or through it. So if it bounced off of it, that would be reflection. If it goes through it, that would be refraction. So if it encounters an obstacle and essentially either kind of like goes around or goes in between, that's when we get diffraction happening. So as an example, we had a whole lecture about sound and understanding that sound is a wave, and being a wave, it diffracts, which essentially means that when it goes close to an object or through an opening that is roughly the same size as the wavelength of that wave, it's going to sort of turn around that object, or sort of bend around that object. Or if it's going through an opening, it's going to sort of bend outward. It's going to sort of expand outward. So for instance, when you're talking, if you were at like a street corner and you're on one side of one side of a building, someone on the other side of the building, you can be talking and that person will hear you, right? That might seem a little bit odd if you think about it, because when you're sound waves, when you're creating these longitudinal compression waves with your vocal cords, those waves are propagating outward. And if we just thought about like reflection, refraction, then when they hit the wall, they would maybe bounce off. They probably don't go through the wall, so they're not going to refract. And you might imagine that there would be sort of like a shadow cast around the corner of the wall where the waves are going to kind of just not really get to, because the wall's blocking it, basically. As it turns out, and as you probably know, you can hear people around a corner, and that's because the sound waves diffract around the corner. So sound waves are, as we talked about before, they're on the order of like an inch to, several yards, something like that. So the size of a sound wave is roughly on the order of like the size of the wall there, which means that diffraction is going to occur when that sound wave is of a similar size as the object. So sound waves diffract, and in this case, they actually sort of bend around that corner, and you can hear the person that's around the corner. So that's sound waves, but like I said, all these waves diffract, and we're mostly talking about light in this lecture here. So other instances of diffraction would be like these kind of diagrams here where in A there you have this wave coming along. You can imagine maybe it's like a big ocean wave, big long water wave, and there's a big barrier, and when the wave hits that barrier, well, some of it's just going to hit the barrier, it's maybe going to reflect back, but the stuff that goes right around the corner, when the wavelength, so like the distance between those lines is the kind of like the wavelength in this picture, is about the size of that object, the wave's going to diffract and it's going to sort of bend around the object. Right? It's going to sort of spread out after it gets past the object. The same sort of thing happens if you have a wave that's encountering like a circular object, like in B here. And again, the wavelength, the distance between those kind of lines that is indicating the wave, is about the size of that obstacle. And so when it encounters that obstacle, it's going to actually bend, since it's a circular object, it's the wave on either side of it's going to diffract, and they're both going to sort of curve in as they pass that object, that obstacle. So those two examples are where you have an obstacle that's about the size of the wavelength and you get diffraction. It turns out if your wavelength is much, much shorter or smaller than the obstacle, or if it's much, 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 much larger than the obstacle, you don't really get that much diffraction. So the picture in C here is I have that same sort of circular obstacle, but now I have a wave coming in, and the wavelength is very, very short. Right? The distance between those wave sort of crests is very, very short. So when it passes that obstacle, instead of diffracting as it did in the other one, that difference, that vast difference in size between the wavelength and the obstacle that's going past, means it doesn't really diffract very much at all in this picture. So diffraction would mean that it would have like turned and curved around that object a bit. Okay, so as I mentioned, the diffraction occurs not just when you're going around an object or by an object or trying to pass by an object. It occurs if you go through an opening. So, for instance, sound, when it goes through a doorway, again, or like an open doorway, again, people could be on the other side of that doorway and they could be out to the side of the door and they're still going to hear you. That's because when the sound wave goes through, it diffracts and it actually spreads out in both directions outside the doorway. Similar to the picture sort of on the top here, kind of what I would be saying here, where you have a sound wave coming into this doorway and then it spreads out on the opposite side as it goes through. Again, how much diffraction happens depends on how close in size the wavelength of that wave is to the size of the opening. So in the top picture here, you have a narrow slit that's, the slit's about this big. Looking at the wavelengths, it looks like the wavelengths are a similar size, so you get a lot of diffraction. There's a lot of spread as the wave comes out the other side. Versus the bottom picture, you have same wavelength, much bigger opening, right? So the wavelength's much, much smaller than the opening. You don't really get much diffraction. You still get a little bit. It still starts to spread out a little bit, but it's not very much. And as a more realistic image of that, you can look at things like when water or ocean waves or any kind of water waves pass through an opening, like if you have these two big rocks, there's waves that are going to be coming into those rocks, and as the waves hit the barriers on either side, there's this opening, and the wave continues to go through, but it diffracts as it comes out, right? So it comes out and it sort of spreads out as it moves past the opening. Okay, so let's look at some actual moving waves and see what that looks like. Okay, so just to warn you here that there's also not just waves like we were talking about already, but there's some other kind of images in here might not say as much about until later. But this first one is basically that wave, right? So again, those dark areas are like the wave crests maybe, and so that's can show you pretty much the wavelength. The wavelength is maybe this big. The opening that wave is going through is much larger than, good bit larger than the wavelength. So you see when it comes down the other side, there's not much diffraction. And well, what this is basically a water tank, and you're using a projector and some mirrors to project the shadow of these waves, and you can see what the waves are doing. So this is one example. It's going to switch up pretty quickly. All right, see it switched up already. And now the opening is much smaller. It's kind of more on the size of the wavelength, and so you get much more of this diffraction happening as the wave passes through. This video, the clarity is not very great. It's one of the best I can still find though to show this, so I would highly recommend you pausing this video and following the clip to this one and actually watching it directly. There we have something we're going to talk about right now. So one more example of diffraction where we're not going through an opening anymore, it's the wave that's encountering this obstacle and going around the obstacle. So you have, again, the same kind of wave, very similar wavelength, encountering this dark spot, this obstacle here, and as the wave encounters it, it diffracts around either side and starts to kind of enclose the object a little bit. The object's pretty big compared to the wavelength here, so there's not as much diffraction, versus if the object was maybe half the size, you'd see even more diffraction happening. Okay, so one of those images, or maybe two of them, was a wave coming into a barrier, and that barrier had two openings in it. So this becomes a pretty important thing moving forward. There's a very famous experiment that was done with waves moving through these sorts of two openings in a barrier, and the openings were, when you're using light waves to go through that barrier instead of water waves, those openings have to be very small, because light, the wavelength of light they're using, is generally very small, so you got to get the opening to be kind of that size. So usually that kind of experiment is called a double slit experiment, where you have slits, very narrow slits as your openings. So what happens when a single wave encounters a barrier with that two openings? Well, as shown in the picture up here, you get diffraction out of each of those openings. So at the top, you get diffraction coming out, you get the wave coming through, diffracting and spreading out. At the bottom, you get the wave diffracting, spreading out as well. Right? Same thing happens in both of those places. But now, on this side of the barrier, it's almost like you have two waves that were emerging from these spots. These two sort of circular waves that are coming out of those openings. And recalling from, I don't know which lecture it was a while ago. Maybe it was a sound lecture where we specifically talked about interference of waves. Yeah. And how waves, when you have more than one wave, they can interfere with each other, meaning they can essentially kind of add to each other and make the wave larger in a sense, or subtract from each other and sort of cancel the waves out, cancel each other out. So when two waves do this, or more than two waves, as you might realize now, it can be more than two waves can cause an interference pattern. But if you just say have two waves encountering each other, they're going to create what we call an interference pattern. And that's essentially an alternating sort of set of these constructive and destructive areas where the waves add together or where the waves cancel each other out. And hopefully you recall from that sound lecture there was a demo or demonstration that had two speakers, right? So giving off these sound waves, and a microphone that was in front of those speakers, and you're moving the microphone back and forth. And what was shown in that demonstration was that as I move like left to right horizontally in front of these speakers, I encounter areas where the sound is very loud, and so you get like this constructive interference. Those waves, the sound waves are adding together and becoming even louder. And then you get areas where there's almost no sound at all. It gets very, very quiet as you kind of move to the side here. And that would be the destructive interference, where the waves essentially cancel each other out. And that pattern kind of repeats itself. It's very, very loud right in between them, gets quiet, gets loud, gets quiet, gets loud. It does this sort of pattern. We call that the interference pattern. So for water waves, if you were to have an interference pattern like that for water waves, so say the picture up here was water coming into this barrier, diffracting out of the two openings, and interfering, you'd get the constructive and destructive interference. And for water waves, that just means you get very high, the constructive interference is essentially where the water is much higher up, and the destructive interference is where you just have flat surface, right? So the waves can cancel each other out. For light waves, constructive interference essentially means a brighter area, brighter spot. Destructive interference means no light at all. You have zero light waves there now when they're in that destructive sort of pattern. And you get dark spots, places where no light is. So the bottom here is an image of imagining these are now light waves that are coming at this barrier with these two slits in it, and they hit this sort of photographic plate or photographic film, and then on the very far side you have sort of the film turned towards us so you can see what the bright and dark pattern is on that. So when you have light coming through this double slit, what you end up getting is this interference pattern when the light all finally hits, which is very bright in the middle, and then it goes dark, where almost no light, and then bright again, and then dark, and then bright again, and then dark, and then bright, and it's kind of dying out as you move further and further away. Okay, so this is a nice little visualization of this experiment, and it shows a number of different things, but the first thing it shows is actually imagining what would happen with this sort of experiment if you were using particles. Particles being like balls, like billiard balls. So if you had a source of these balls and you were just shooting them at these openings, what sort of pattern would you get at the other side? So if you're just shooting these balls, like tennis balls, at these openings, some of them are going to go through, some of them aren't going to go through. The ones that go through land somewhere, the ones that don't go through get knocked back. And in the end, there's no real pattern there. So that's with like particles, like tennis ball kind of things. What about with waves? So now we have a wave hitting these double slits. It's going to diffract out of each of them. We're going to get this interference pattern on the other side. So where the waves are interfering constructively, we get these bright spots, indicated by the orangish color here. So right in the middle, you get a very bright bar. Then where they're interfering destructively, you get these dark bands. You get no light shining or landing there. And you get, again, that bright and then dark and then bright and then dark and bright. You get this interference pattern showing up. Okay. So this property of diffraction is a property of waves. Like all water waves, sound waves, light waves. All those things diffract. Particles, like balls, don't diffract. So a particle will either make it past an obstacle or it doesn't make it past an obstacle. There's no bending around the obstacle. So the comparison would be like a wave from the first image, or one of the first slides. You have a wave encountering this obstacle. When the wavelength is about on the size of the obstacle, then you get this diffraction and the wave bends on the other side as it moves past. It kind of spreads out again as it moves past. For balls, particles, you're basically just shooting a bunch of tennis balls at an obstacle, and the ones that are not going at the wall are going to go past it. You get the ones that are going at the wall, get knocked back somewhere. So you only get those balls hitting on the other side. There's no bending as they go around. There's no diffraction. Right? So same thing for these double slit setup, or these two openings. So a wave, like light, will create this interference pattern where you get these bright and dark bands. And balls, no interference pattern. Again, the ones that go through. The ones that are going at the barrier get knocked back by the barrier. That's pretty much all there is to it. Okay, so as a quick question, we'd say this phenomenon of interference, this property of interference, it occurs for which of these things? What would you say? Go ahead and pause, maybe you know right away, but if you don't, take a second and think about it. So hopefully you said D. All of these, interference will occur with all of these things because they're all waves. Okay. So it might seem weird why I'm pushing this point so much, but well, you should understand why just a little bit later in this lecture. So the point of all that is to say that light is for sure a wave. Light, it has a wavelength, and for light that wavelength varies from very, 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 very small wavelengths, like gamma rays, all the way through visible, through microwaves, radio waves, and so radio waves all the way on the other side, very, very long wavelengths. It has a period of oscillation, it has a frequency of oscillation. Right? So it has these period, it has frequency, it has these properties. It refracts, it diffracts, these things that waves do. And as I was just pointing out, it forms interference patterns. And the sort of more technical term, or a technical term within that sphere of interference patterns, is to say when two waves are sort of interfering with each other, and they're sort of on top of each other, or in the same space, we say that they are superpositioned, which is a just fancy way of saying they're combining. Right? So the superposition happens with these waves. And you get these constructive and destructive interference patterns. Okay, so light definitely acts like a wave, for sure. All right. Now we're going to switch gears slightly and talk about some other properties of light. And yeah. So specifically having to do with the emission of light, or as light gets emitted from things. So if you recall from our lectures about heat, you will know that all objects give off light in the form of infrared light, or you could call it infrared radiation. And as it turns out, the hotter an object is, the higher the frequency of light it's going to give off, meaning higher frequency, meaning shorter wavelength of light. And not only is it going to give off a higher and higher frequency of light, it's going to give off more and more light as well. So more and more of that radiation, that light electromagnetic waves, are going to be emitted as you heat up an object. So as an example, if you take steel, right, steel at room temperature is giving off infrared radiation. It's giving off light in the infrared range. We don't see that. Our eyes don't see infrared radiation. What we see is light that's coming from elsewhere and generally just reflecting off that steel and hitting our eyes. So we see the light because the steel because other light is bouncing off of that steel and coming to us. So take that steel and heat it up a lot. You heat it up to about 1200 degrees Fahrenheit, it glows red, meaning you've heated it up so much that you've increased the frequency of that light that's being emitted from it, so much that you push the light from the infrared range into the visible range, and particularly red light. Yeah, so red is a higher frequency light than infrared. So heating it up, it's getting the higher frequencies of radiation it's giving off, light that's giving off. So you keep heating it up even more. It's going to give off, well, you get up to about 2000 degrees Fahrenheit. It turns out that it's going to radiate yellow light, right? It's going to glow yellow. And you get yellow is even higher frequency than red light. And it's actually going to give off even more light in general, a lot of yellow light versus just some red light. At the bottom here is just kind of a chart that actually is used, I believe, by either people, metallurgists or blacksmiths or something, so you can actually tell roughly the temperature of steel by what color it is. And that's because of this property that it emits higher and higher frequency light that eventually kind of pushes it from infrared into the visible spectrum, and we get visible light out. So this property has been known about for a long time, this emission of light from heated bodies, from things that are at very high temperature. And the way to explain that, well, before the 20th century, there were sort of two explanations of why that, not really explanations, or two ways of looking at why that occurred. And the problem was that neither of them could explain the whole kind of phenomenon. So one could explain it sort of at a very, at sort of lower frequency range, one could explain it at higher frequency range, but neither of them could meet up. And the one that explains at a lower frequency range, or a longer wavelength range, so it tends to fit very well for longer wavelengths that are emitted for bodies that aren't heated up that much. If you start to heat up a body a whole lot, then you're getting to shorter wavelength light that's going to be emitted, and that theory, the explanation of it, broke down. Essentially, what that theory was saying, or did say beforehand, was that if you heat up a body enough, it's essentially going to emit an infinite amount of light. And not a crazy, you don't have to heat up a crazy amount, right? This chart is showing, it's maybe difficult to interpret if you're not used to looking at graphs or charts, but essentially the red, the green, the blue, and then this black line are are just different temperatures that say you've heated steel up to. Right? So you heat steel up to 3,000 degrees, then the wavelengths of light it's going to emit are mostly sort of around 1,000 nanometers is what this chart is showing. You heat it up to 4,000 degrees, you're going to get more light out of it, the bump is sort of higher here, and the wavelengths are even shorter. You heat it up to 5,000 degrees, you get even more light out, and the wavelength is shorter again. The black line is what's written on there is the classical theory. This is the theory I was talking about before, where at shorter and shorter wavelengths, this theory started to predict that you'd get this infinite amount of light coming out, and particularly ultraviolet light. Okay. So these colored lines are the modern predictions, and they fit very well with what actually happens in the world. this line is essentially showing that even if you got an object to 5,000 degrees Kelvin, which it's a few thousand degrees, several thousand, or 3, 4, something like that, 1,000 degrees Fahrenheit, then you'd expect to just get an infinite amount of ultraviolet light coming off of this object. That's an issue because we've never actually observed an infinite amount of anything, let alone an infinite amount of ultraviolet light. So, since the observations never saw this, and since we've never seen this, this was known to be a problem, and it was actually called the ultraviolet catastrophe. It was a catastrophe because once you started radiating ultraviolet light, it turns out that that theory was saying you'd radiate an infinite amount of ultraviolet light. It's a very short way of saying that. Okay. So that was sort of pre-20th century, right around the turn of the 20th century. At the beginning, and right around that, or I guess around that time, somebody started to come up with a resolution of this, or how we resolve that problem. There's actually a guy called Planck, and he basically postulated or said, well, maybe light only comes in specific packets, like just chunks of light. Right? So we talked about that idea of chunks of light before. We called them photons. So the problem, that ultraviolet catastrophe, was a problem if you assumed that light came in any range of frequencies. You could have as small a variation of frequency of light as you'd like. It doesn't really matter. If, however, you start to say that light only comes in certain chunks, right? I can't have like this that amount. I gotta have something a little bit bigger than that, right? It only comes in this certain amounts. Right? If you say that, then it turns out you can create a theory to explain this emission of light, right? So like a theory that predicts the ultraviolet catastrophe, but one that actually fits the data. Right? So one that does explain things. So that is basically, that was evidence that light actually comes in packets. Right? It comes in little discrete chunks. And we call those chunks now photons. A photon is a particle of light. It's a chunk of light. So the image here is just a picture of a laser. A laser, you can kind of think about it as just like a stream of photons, a stream of identical photons, like here a stream of green chunks of light. So this is in contrast to waves, right? Where the frequency of a wave, it seems to be a continuous thing. There's there's no limits on what frequencies you could have for a water wave or for a sound wave. Okay, so another thing was happening, or being looked at around that same time, and that was called was known as the photoelectric effect. So this phenomenon had been known about for a while beforehand, but never really understood or explained, like had a good explanation for what it was or why it happened, or maybe more why it happened. They kind of knew what was happening, they just didn't know why it was happening. But essentially the phenomenon was, if you take ultraviolet light and you shine it on some surface, mostly like metals will do this, then it turns out that you can essentially knock electrons off of that surface. And so like the picture down here, you see like light rays coming in, hitting this surface, and you get electrons that are being emitted out, they're being kicked off of that surface. So this could be useful if you say put that metal into a circuit. So remember back from our talk about circuits, where if you have a movement of electrical charge, an electron is an electrical charge, it's a negatively charged particle. If you have a movement of electrical charge, then you have a current. Current is just a flow of electrical charge. So you put that metal into a circuit, you shine that ultraviolet light on the metal, and you can actually get a current to start flowing in this circuit. that the electrons that are knocked off that surface can then go to this sort of far other piece of metal here and get pulled onto and kind of start flowing around this circuit. This is actually the basis for how we generate solar power. Right? Light from the sun, ultraviolet light from the sun coming down, hitting a solar cell, knocking electrons off, and you collect those electrons in some way and flow them to be your current. Right, so there's a particularly interesting thing that happened, or didn't happen, with this photoelectric effect. And that was, like, as I said, you kind of need to shine something at least like ultraviolet light, which is pretty high frequency, pretty short wavelength, on that surface in order to knock the electrons off. It turns out that if you shine light that's at a lower frequency than that, kind of below this sort of threshold, lower frequency, longer wavelength, then you don't get any electrons coming off. And it doesn't matter how much light that you shine on that surface, as long as the frequency is too low, you're not going to eject any electrons. So in this picture here we have, say, some high frequency, short wavelength light. You kick off electrons, and as it turns out, the higher the frequency, the faster those electrons get knocked off. In the middle we have lower frequency, a little bit lower frequency, a little bit longer wavelength light, but it's still high enough frequency that you knock electrons off. It just turns out that those electrons are moving a little bit slower now. You go below a certain threshold in frequency, and you don't get any electrons coming off. Again, no matter how much light you shine on that, it's not going to knock any electrons off. Or how much light of that lower frequency. So what does that mean? Well, the amount of light that you're shining on an object is, if you shine more and more light on it, it's sort of like, shown in the picture here, it's like a water wave that's coming in, and more light is sort of like higher and higher amplitude of the water wave, right? A larger and larger water wave. So not having to do with the frequency or the wavelength, just larger and larger amplitude. And for water waves, if you have a very large amplitude of a water wave, a very large wave, it's going to be very powerful. It has a lot of energy in it, and the larger that wave, basically the more damage it's going to do. Okay? So with a regular sort of wave, if you have, your average ocean wave coming in, hitting some barrier, maybe the amplitude is a couple yards, something like that, doesn't do a whole lot of damage. If you blow that amplitude up to sort of, I don't know, movie-like tsunami type wave in the second one here, right? Enormous amplitude, then it's going to do an incredible amount of damage. It's going to knock buildings over left and right. So the thought was for a while that even though you have a lower frequency of light, if you shine enough of that light on, you should dump enough sort of energy onto that surface that you would knock electrons off. If light was being just like a wave, that's how you would expect it to act there. Just shine enough light on, you get a large enough amplitude, dump enough energy there, you hit electrons off. That wasn't happening, right? It didn't matter how much of that low frequency light you shine on that surface, you don't get electrons coming off. So this was essentially another example, or another observation, thing that was happening, this phenomenon, that was saying light actually isn't acting like a wave. It's acting more like a particle. So, from the resolution of that ultraviolet catastrophe, it turned out that light, it would make more sense, it would work out with observations, if you could say light actually came in packets. It was photons, right? It was like chunks of light. And from the photoelectric effect, it was turning out that, again, light was acting more like it came in chunks. It wasn't acting like a wave. So both of those examples, or both of those things, and the resolution of those things, was telling us that light doesn't actually act like a wave there. Light acts like a particle there. So what's going on? Some places, light acts like a wave, big ocean wave like that, like you would say. Other places, it acts like a particle. And remember, a particle, just think of it as like a ball. A billiard ball is a great example. So, as it turns out, one of the ways that, or one of the things that brought about what we call modern physics, or our modern understanding of the world, is to essentially accept that both of these statements are true. Light will act like a wave, light will act like a particle. And it turns out that that acceptance of, or the acceptance of that idea is one of the core principles of quantum mechanics, or quantum physics, you might say. So just to be clear about this, when in our normal everyday life, we basically encounter two kinds of things. We encounter things that act like particles, like balls, like billiard balls, and we encounter things that are like waves. So particles, well, they're essentially things that are like confined to a space, right? So again, think of like a billiard ball. It only takes up this certain amount of space, and if I can point to it, that's where the particle is. So that's where the billiard ball is. And I say it moves in a singular way, meaning it only moves one way at a time, right? If I have a billiard ball, it's moving, it's going to move in that direction, right? Or it's going to move in that direction. There's no sense that it's going to move that direction and that direction. And if you think back, the first part of this course was mostly focused on things like particles. Right? We were talking about things moving, objects like cars rolling down the road. Right? Cars, sort of like a particle thing. It's a thing that's confined and it moves in one direction at a time. Later, more recently, we started talking about waves, right? So waves are things that can actually just be spread out through a very large space. An infinite amount of space, actually. Don't worry about that. But it's essentially, it's the opposite, right? It's not confined to a space. If you have, say, like an ocean wave, imagine looking out from the shore and you see a large, big ocean wave coming into the shore, there's not really the same sense as like with a billiard ball where I can just point and say, there's the wave. It's right there, right? So in that sense, the wave is spread out over this whole overall, this very large space. And beyond that, waves can actually move in many directions at the same time. So like this picture here, if you drop a rock into a pond, you create these ripples, which are waves, and they spread out over space, right? But I can't really say what direction the wave is going in, right? Because each part of the wave is actually going in different directions. Right? The part on the top is going up, the part on the bottom is going down, the part on the left is going left, the part on the right is going right. Right? It's spreading out in all directions. So again, it's very counter to a particle, where a particle moves in one direction at a time. Yeah, so more recently, this course is focused on waves. Okay, so before moving on, quick question for you. Which of these things is an identifying property of a particle? What's something you could say that's particle-like? So take a second, pause, and give your answer. You got it? Right, and so hopefully you said B, it only moves in one direction at a time. So again, when you think of a particle, when you hear particle, think of like a billiard ball. Billiard ball only is going to move in one direction at a time. It can't move left and right at the same time. Yeah. Okay. So getting back to this idea where we kind of have to accept that things like photons can actually be particle-like things at one point and wave-like things at another point, different times. Well, if that's doesn't seem odd to you, then maybe we're getting just into an era where this has been sort of not necessarily common knowledge, but known of for long enough where it's kind of not really taken as being that interesting anymore. I hope not, but we'll see. So anyway, in sort of normal circumstances, right, where we're talking about like people and cars and planets and dust and things like that, right, objects are generally just gonna fall into one of those two categories, being like a wave, being like a particle. Right? So billiard ball, car, chair, person, those are all particle-like things, where sound waves, water waves, seismic waves, those are all waves. As it turns out, that when you get to things that are very, very small, like incredibly small, like photons, this sort of way of categorizing things just doesn't work anymore. It's not correct at all anymore to say that this thing is a particle or this thing is a wave. And it turns out that it's not just for very, very small things that this is true. There's other classes of things or places and things where this is also the case. But thinking about, it's a very kind of straightforward example of it, right? The most sort of straightforward. Just think this happens when things are incredibly small, right? Like the size of an atom or smaller than an atom. So with things that are that small, you get just them acting one way or the other. And it depends on sort of how you look at it, the way you try to observe it. Right? So if we observe light diffracting through those double slits, it interferes and it looks wave-like. It does this wave-like thing. If you observe the photoelectric effect, it doesn't act like a wave, it acts like a particle. Right? So it depends on how you're trying to observe something. This is often referred to as a particle wave or wave-particle duality. And at the bottom here, just giving you some scale, the numbers are in meters, so a person is sort of on the meter size scale, about a meter. Go further down, you have these like red blood cells, which are at 1,000th of a meter. Go even further down, talking about atoms, and even further below that, you get into the pieces of an atom, like a proton, or the pieces of a proton, which we might talk about later. But yeah, so essentially once you get to that sort of atom scale, now we're talking about things that are no longer just like particles or just like waves. There can be either one of those things. So, as I mentioned, the timeline, this was sort of early 20th century when these ideas were coming about, and there were actually a lot of people that were involved in it. There were some very big names still, and one of them was this guy Niels Bohr, and he kind of thought about this wave particle thing in a way that he called or a sort of a way to understand, a way to accept it, with this idea of complementarity. So complementarity is essentially when you have two ideas that seem to contradict each other, but are actually properties that can coexist. And indeed, those properties can actually complement each other, right? So that's what we call complementarity. So just because we encounter things on our everyday scale that are either wave-like or particle-like, it doesn't actually mean that things on every scale have to be like that. And in fact, just been saying, at a very, very small scale, that categorization just no longer applies. And just interesting stuff, he adopted this coat of arms, which has the yin-yang symbol that he liked to use for the complementarity, right? These two pieces that are part of the same whole, opposites but part of the same whole. And the slogan or the mantra or whatever it's called translates to opposites are complements. Alright, so given all of that knowledge, it's probably a good time now to go back and revisit this double slit experiment. Because as I mentioned I think earlier, some very interesting things can be gleaned from this experiment. So, as I pointed out, right, essentially when photons are leaving things, like being emitted by things, or when they land on things, getting absorbed by some things, they act like photons. Right? So when you have this double slit experiment, essentially what you have is you have a source of light, then in front of that source of light you have a barrier with those two openings, those two slits, and through those slits the light waves can diffract and interfere with each other. And finally you have this screen, or generally a photographic film, such that, well, film so that when a photon lands on it, it leaves a bright spot. Right? So getting ahead down the bottom are pictures of a photographic film that's being exposed to the light in this double slit experiment. So on the left you see just like, it's like a few photons have hit. Right? So that's what it looks like. You just got a bright dot there. Okay, so when the light is leaving the light source, it's like a photon, it comes off in chunks. When it lands on the film, it hits in chunks. However, when it's in between, we know that it has to do some kind of interference. It has to do, or else we wouldn't get this interference pattern. So in between, it's actually acting like a wave. So in this one experiment, or in this one sort of setup, you see light acting as a particle at one point and a wave at another point and then a particle again. And it becomes even more kind of curious if you sort of turn down, like crank down the power of that light source, and if you crank it down enough, then basically you can get to the point where only one photon at a time is going to be leaving the light source and eventually hitting that film. And then after it hits that film, another one comes off and then eventually hits that film. Right? So you crank that power down enough, the intensity of that light source down enough, where there's only ever, say, one photon that will have left and arrived at a given time, or in a time, right? So there's only one photon in there, in this whole sort of setup. However, even if you do that, so you know that there's only one photon that left the light source, there's only one spot that appeared on the film at a time, if you just do that and let that play out, so you get one photon leaving, arriving, next photon leaving, arriving, next photon leaving, arriving, you still build up an interference pattern. So the pictures on the bottom are just the progression as you let more and more photons leave the source and arrive at the film. Right? So to begin with, in A, there's, I don't know, maybe 2 dozen photons that have left the source and arrived at the film. Right? You don't really see much of a pattern there. However, you keep letting more and more photons go, and eventually you start to see this pattern emerge, the same interference pattern. And this is only with one photon moving through this whole apparatus at a time. Well, it's kind of odd because, well, you might think, well, maybe, it's one photon, it leaves the light source, it goes through the top slit or it goes through the bottom slit and it hits the screen. Okay. Well, if you assume that it's going to go through just one of those slits, you can assure that actually just by blocking one of the covers, blocking one of the slits. Right? Put a black piece of paper in front of it. No more photons going through. Right? If you block one of the slits, it turns out you destroy that interference pattern you had. You don't get that same interference pattern anymore. So it's not the case that those photons each photon is going to go through one or the other of the slits. The only plausible conclusion is that one photon leaves the light source, it propagates through that apparatus, through the screen. It diffracts as a wave and interferes with itself on the other side of the screen in order to say where it's finally going to land is somewhere in that interference pattern. Right. So if you're not getting how strange that sort of is, then there's a very nice or kind of neat idea or a way to explain this, which would be, I call it the quantum rocks picture here. And essentially this would be like if you take a rock and you're at the edge of a lake and you throw the rock into the lake, right? So in the experiment, that's like the photon leaving the light source. You throw the rock into the lake, you make ripples, right? You cause these water ripples, these waves to move out from where the rock entered the lake. Right? That's like that photon propagating through the screens and whatnot. And eventually, those ripples, those water ripples, are going to start running into the far shores, right? Some beach or some rocks or something eventually further out there on the other side of the lake. At that point, all of those ripples condense again and the rock pops back out and lands on the shore somewhere. There you go, that's like the photon hitting the screen somewhere. So a very sort of odd thing. You'd never see that on our scale, and for reasons that I'll get to, I think, in the next lecture. But that's what it would be like if you, say, had a rock and a lake and it was acting like a quantum sort of system. So it turns out this same visualization, it actually does this kind of picture too, where it's not just showing you how particles go through this double slit experiment or how waves go through this double slit experiment. It gives you actually a pretty nice visualization of how a quantum object, like a photon, an actual photon, will go through this experiment. So it sort of leaves in a piece and then spreads out and moves as a wave, goes through this screen as a wave so that it interferes with itself on the other side, and then bam, lands at one spot on the screen. There you go, there's another one. Right? And they're showing here that wave that actually moved through, interfered with itself, and you keep letting these photons go through, and it's showing that you're going to build up this interference pattern again. All right, so something you might be asking yourself as, you know, person who lives on a very large scale relative to quantum things that are very, very small. Asking yourself, well, where is that photon? Right? As in, I know it left the source, I know it hits the film, where is it in between? Because that pattern that we're getting, this interference pattern, is built up of many, many photons hitting the screen. And to get that interference pattern, we know it has to act like a wave as it moves through that apparatus. As it goes through those slits, it needs to diffract and it needs to interfere so that we get this interference pattern. In that last video, just a second ago, when the wave finally reaches the screen, it sort of just condenses and then it lands as a single photon. Right? It lands as just a bright spot on the screen. It turns out where that spot is going to be, where exactly any particular photon is going to land, you cannot say. There's no way to say beforehand that this photon that's leaving the source is going to land at that particular spot on the screen. What you could say, well, you can say that a lot of them are going to hit right in the middle, because that ends up being the brightest spot in the interference pattern. Overall, less and less land as you move further away from the middle. It gets dimmer as you move further away from the middle. And we could say that there's bands, there's these dark bands, where none of them are going to hit at all. And if you'll notice, all of these statements are statements about probability, about what is possible to happen, and even a little bit beyond that, how likely is it to happen, right? Like I said, most of them are probably going to hit, a lot of them are going to hit in the middle. It's pretty likely they're going to hit, when one leaves, it's going to land in the middle. It's pretty likely. I can't say that it will, but I can say it's pretty likely that it will. So as it turns out, something else we can get out of this double slit experiment is the fact that photons don't act in what you would call a deterministic way. Right? There's only, there's a certain underlying fundamental probability or probabilistic sense or way of the photon. And as it turns out, that is essentially the other core principle that underlies quantum physics. And that is that the universe is fundamentally probabilistic, meaning the outcomes, whenever something happens, the outcome is not, you're not able to predict with 100% accuracy. That's not to say that we can't be pretty good at predicting the overall outcome, or in the case where you get away from these very, very small objects, right? You move away from the quantum world and you get to stuff like, kind of human scale or anywhere above the quantum world. It becomes, it comes to the point where the probabilities of other things happening than, say, like me dropping, if I drop an object, it's going to fall. The probability that it doesn't fall is still there, it's just ridiculously small, and it is going to fall. However, on the fundamental scale, on the scale of the things that build up the building blocks of our universe, like photons, it's all probabilistic. There's no determinism. There's nothing you could say with 100% certainty. I think that's what we say. Okay. So, that is it for this lecture. I hope you found it interesting. This is one of my more enjoyable, one of the more enjoyable parts I find about physics. It's something that drew me to physics, so hopefully you're starting to, or you kind of enjoyed this. Right. And so that's going to be all that we're going to talk about, particularly about light. Next lecture, we're going to get into more broadly about quantum physics, and probably also talk about some stuff like nuclear physics, radioactivity, and things like that. So, there you go. Feel free, go and watch that double slit experiment video. Again, I would recommend it. It's pretty well done. And I hope you have a nice day. See you later.